Hello, my name is Ana Cecilia Valdez, and this is my final lab for Physics 2211, Lab 5, Choose Your Own Adventure. In this lab, we are given the freedom to choose our own adventure, so I will be analyzing the motion of a falling slinky. I will be using Tracker to analyze the observed motion of this falling object, and then I will use GlowScript to create a code that models computationally the predicted motion of this object. Finally, the results for both models will be compared, and I will be answering some questions at the very end. As you can see, we have a very interesting motion situation here. First, the slinky compresses gradually from top to bottom, while its lower part remains stationary, and then once the object is compressed, it falls altogether. The formulas and main physics concepts that I will be using for my experiment are the ones that I show in this slide. And well, for this motion scenario, we have first tension uh, with a slinky. The tension force is acting upon the slinky, and then we have a drag force opposing motion, and as we already know, gravitational force is present always throughout the motion. And well, the position and velocity update formulas are just essential to allow us, they allow us to better understand and depict what's happening, how fast and where it is happening. As you can see, the tracker software allowed me to extract the real observational data of motion by literally tracking the changes in position throughout the video. As you can see, this code is a modified version of the code of Lab 2, motion of a falling object. However, now it takes into account that the falling object is a slinky, which is very important. First, I initialized the variables by declaring the slinky's mass, the position vector of the slinky, and the velocity vector. Also, I stated the acceleration due to gravity, and I calculated the proportionality constant, which is b, with some trial and error. For the first part of the motion, I used a while loop that considers the bottom part of the slinky to be stationary. In this part, as you can see, the tension force and the weight force were calculated in order to obtain our net force, and then with these variables we can calculate again the velocity and the position with the position and velocity update formulas. For the second part of the frame, I did another while loop. For this scenario, the forces change a bit, as you can see. We still have the force due to gravity. However, we no longer have tension, and instead we account for drag force, FP. Now, considering these changes, we calculate the corresponding net force for the second part, as you can see, W plus Ft. And once again, position and velocity are calculated for this corresponding second part with the position and velocity update formulas. As you can see, this is a predicted motion depicted by the computational model. We have this position versus time graph that shows how movement is constant, and then the slope turns negative. So now let's discuss a little bit our results. Well, we have our graph in the left, which is the one we tripped from Tracker, and a graph in the right, which is taken from GlowScript. Basically, our observed motion is in the left and our predicted motion is in the right. And as you can see, they both follow the same basic pattern. Both of these graphs agree that the slinky remains stationary, and then once it's compressed, it travels constantly in the negative direction. And well, part of discussing this data in this conclusion is discussing the possible sources of error. And well, one of these is that we might have considered a perfect system where drag is constant. That's why um, the tracker and the other closed script model are not exactly the same, because the closed script model visualizes something in a perfect system. And well, also like in tracker, we could have some anomalies in the process of tracking and just some filming errors. Just a slight movement in the camera can compromise a little bit of the data, but overall we can see that the graphs agree with each other. Just to wrap up this lab, and we will answer some questions. And well, the first one, why is the bottom of the slinky stationary before falling? The answer to this is that the slinky remains stationary before falling because at the beginning, tension and gravity are opposing forces of equal magnitude, and therefore they cancel out, which makes that the bottom of the slinky stay stationary. However, in the second part, the force of gravity is greater than drag, which makes it move as we see in the videos. And what if there was a mass or ball at the bottom of the object? Will it still be stationary? The answer is yes. Even with a ball, it will stay stationary because the system works the same way. The slinky won't move until it is compressed with or without a ball.